Hello everyone, good morning. Today we are going to start with our lab number 2 of mechatronics. As you can see on the CAD courses, the lab was uploaded yesterday. Yes, yesterday was uploaded the lab. Let me share my screen. Let me share my screen right now. Can you see my screen? Let me put my chat box over here. Okay, good. This is, we can go to assignments, and in assignments, go to laboratory, lab 2 is in the bottom. Let me just show you the lab assignment. The lab assignment is basically the foundations of Matlab and Simulink, how we can build simulation models with Matlab and Simulink. We are going to start today with a simple example. You can access to this link. This is a tutorial that we prepare for you. This tutorial takes about 52 minutes and contains all the foundations that you need to start making Simulink and Matlab is coding for control systems and its applications. So today we are going to see this video first before at the beginning of the class after my speech, and then you are going to have the rest of the time of the lab to work on the lab assignment. The first part of the lab assignment, you have to replicate the tutorial. All that you see on the tutorial, you have to replicate and make some changes according to that you see on the tutorial here. The second part, you go to this website. On this second part, we are going to model a more complex system, Rlc circuit. And basically using this Rlc circuit, you are going to find the transfer function and the differential equation for the circuit. And using the differential equation of the circuit and the transfer function, you are going to build the same but in Simulink, using the same tools that we learned from the tutorial. That's the main idea. So before beginning, I'm going to make a poll for you first. Let me I just launched a poll. Have you ever used Matlab Simulink before? Okay. According to the participants that we have right now, 81% manifest that yes, you use Matlab Simulink before. Some of you manifest that doesn't use Matlab or Simulink before, so no worries with the tutorial. We hope that you can get the basics for Matlab and Simulink in order to run these simulations for controls and mechatronic systems. Okay. I guess we are 19 people. I guess all of you already answered the question. So let's finish the poll. I'm going to play the video. Let me just verify that everything is allowed to share sound. Yeah. Okay. It's nice. Hello everyone, my name is Jairo Viola and today we're going to have our... Can you hear the recording? Excellent. First laboratory titled Matlab Simulink for Mechatronics Part 1, in this case, is based on basic simulations of control and dynamic systems using Matlab Simulink tools. This is for ME142 Lab for this week, February 1 to 5th from spring semester 2021. The learning objectives for today are introducing Matlab and Simulink as fundamental tools for mechatronic and control system simulation, modeling, and design. Acquiring basic simulation skills for dynamical system response analysis through Rlc Circuit, and using Matlab Simulink simulation skills to represent more complex systems, in this case, an Rlc circuit. As you can see, Matlab is a huge software with tons of toolboxes that we could use and can be fit according to our research field. This is just an example to show directly from MathWorks website how many toolbox we have. If we count, we can see that more than 140 toolboxes are available for all the science and engineering areas. So it's huge, Matlab. From biology to communications to to semiconductor design. So which tools we need in that sea or ocean of tools? What are the tools that we need in particular for mechatronics? We can simplify those tools into these 5 groups that we have here. One group is the signal processing, the control systems, physical modeling, math and optimization, and AI, data science, and statistics. Those are like the main toolboxes that we are going to use for modeling mechatronic systems. And inside those 5 groups, you can see that we have like more than 20 toolboxes that we can use. For today class, and of course for the following ones, we will focus on signal processing toolbox, control system toolbox, that will be one of our main toolboxes, as well as system identification toolbox, Simulink control design, Simulink design optimization. This last one will become more relevant when we start talking about digital twins, Synscape to perform the robust simulation models that we need for digital twin. And the other toolbox, we are going to take different commands and codes that we are going to need according to the courses progressing. So for example, here from AI, data science, and statistics, we are going to use a lot the statistic toolbox. This statistic toolbox has many functions that simplify our work. So this will be one of those toolboxes that we are going to use. However, today we are going to focus more on control system toolbox, signal processing, Simulink control design, and Simulink control design. Those 3 are our 3 key toolboxes for today works. All right. In order to start with Matlab Simulink and starting the best way possible, let's begin with a simple model that all of us know very well. That is the Rlc circuit model. The Rlc circuit model, as you can see, is represented by a series resistance connected with a capacitor, with the resistance with a resistance R and capacitance C for the capacitor. The Rlc circuit has an input voltage source. This input voltage source could be direct current or AC current. And we have as output variable from our circuit the voltage on the capacitor. We can analyze by by the fundamental laws of electricity, using Kirchhoff voltage law, we can analyze this current loop here. If we use the KVL, we can get this equation, which is essentially the total power of the circuit plus the voltage on the resistance plus the voltage on the capacitor is equal to 0. That's KVL. For this type of circuit, RC circuit, the current, the loop current in this case, is given or is driven by the current on the capacitor, that is the changing element on this circuit. Therefore, we can set that the loop current I is equal to the current of the capacitor, that according to the fundamental law of the fundamental equation of capacitor, this is the current of the capacitor over the time. That is the capacitance times the derivative of the voltage of the on the capacitor respect to the time. If we replace this into the KVL equation, we will have an ODE, that is this one here, that represents the behavior of the simple RC circuit, using as changing variable or output variable the capacitor voltage VC. And we have our input voltage here, EI. If we solve the ODE, which in this case is possible, we finally result into this equation, that is the time response of the RC circuit, in this case for the voltage capacitor, for the voltage on the capacitor. As we can see, it has an exponential response that in this case, as we can observe here, it is going to increase with time when the capacitor is charging. This is the charging curve of the capacitor. We start from a time 0 and then we reach a steady state value. Usually this steady state value is the input voltage that we are introducing in the system. From this equation, we can calculate the time constant for the RC circuit, which is the product between resistance and capacitance, the RC. This tau or time constant is going to be really useful when we want to model the system for control purposes. The meaning of this tau means that is the time for the RC circuit that takes to reach the 63% or about 63% of their steady state value. For example, if in this case this value is 1, once we reach 0.63 volts, it means that it will be possible at tau equal to RC, that is determined by the resistance and the capacitance. Based on this tau, we can set a rule that establishes that after 5 taus, our system will going to reach the steady state period. So this tau, for example, here is 1 tau, and after 5, as you can see here, we reach the steady state period. Remember this property because it's really important in this type of systems. This is like a first order ODE system, and this will be really important for its modeling in future applications. If we do the same, but in the discharge curve for the current, you can see here that tau is exactly the same. In this case, tau is when we reach the 37% of the current. I mean, the current starts with a peak and then start to reduce based on the nature of the RC circuit. So tau is also useful here to determine how long it's going to take the current to stop flowing in our circuit. All right, so this is our differential equation. This is the RC circuit response. This is the time constant for the RC circuit. Those are like the basic things of modeling that we need to know for this system in particular. If in the case of the RC circuit, It's easy to solve the ODE equation. However, as we increase the complexity of the ODE, could be more challenging solving the equation. In that moment is when Laplace transformation can help us to simplify our calculations towards, in this case, control design and analysis. Using Laplace transform, we can transform the ODEs into a polynomial form in the complex domain S using the Laplace transformation in order to know the response of the to solve the response of the system and understand its fundamental properties. We are going through all the details of stability and dynamics of first and second order systems in next lab. But for today, the most important thing is that we can represent the ODE that we saw on the previous slide using the Laplace transformation. In controls, it's really useful having this Laplace transformation table in order to simplify our control system modeling and design. We can use this table. For example, this is available at this link. Here we have multiple time responses, like for example, square root, sine, or even the derivatives like f prime and f double prime. We can see here the Laplace transformation. For our particular case, these derivatives, f prime and f double prime, will be really useful to simplify. So in this case, we are going to introduce a new concept that is called transfer function. Transfer function in general for any system can be defined as the ratio between the output of the system over the input of the system. In Laplace domain, this is the relationship for transfer function. This relationship is really important because it's going to allow us in the future to analyze the dynamic behavior of the system easily instead of solving the ODE to know if the system is stable or unstable. We can use this transfer function model to determine the dynamic properties of the system. If we calculate the transfer function for our system, where our input is the voltage here and our output is the capacitor voltage, we can say in this case that our transfer function, starting from the converted Laplace transformation ODE, is given by this equation. BCS over EIS is equal to 1 over RCS plus 1, if we solve this equation here. You remember this RC here? This RC corresponds to the time constant of our RC circuit. This is our tau, and that will be the constant that determines how long our system takes to become stable. That's the main point of this RC circuit that we have, RC term that we have here. All right, so we can, based on this transfer function representation, or using the ODE representation, we can use both of them. And we can create that representations on Matlab. And in that sense, we can simulate the behavior. Here is the code for the RC circuit simulation using, in this case, Matlab. I'm going to show you how to build this code step by step in order to get this response that you see here. All right, so let's go to Matlab. That is here. And you can see the code. Okay, as you can see here, this is a tutorial example RC circuit model in Matlab. First of all, if you doesn't have Matlab installed in your computer, you must install the software from UC Merced IT website. You can do it, or you can simply download Matlab from MathWorks website and log in with your UC Merced account, and you have full access to all the toolbox that we are going to need during this course. So if you didn't have MATLAB installed on your computer yet, go and install it, because all our course is going to depend of MATLAB. So let's continue. Here, this is an example of a classic MATLAB code. In this case, here we have these three commands. These three commands, basically, let's add some comments here. This clear workspace. The workspace is this one here. Clear all the variables. Close all. Close all the figures. And CLC, in this case, clean command window. It's a good habit in MATLAB start with these three lines in order to erase any trace of previous trials on the variables. Close all the figures that you could have open from before. You can have many of them, and you don't need all of them, and that make slower your execution. And CLC to clear the command window here below. If you are displaying any result and you don't want to be confused with previous results, CLC is a good way to keep your code debugging and showing your response pretty neat. First of all, we are going to define the RC circuit parameters. As you can see here, here we have the MATLAB script. R, this is the resistance. In this case, the resistance is a 2K resistance, 2000 ohms. This is the capacitance. The capacitance corresponds to a 100 microfarad capacitor. Those are the RC terms on our transfer function. Okay, let's go in this way. Let's put here in this way. Let's go here and here. You see, R is our RC parameters, R and C. Here comes the most important part for defining transfer functions in MATLAB. To define the transfer function in MATLAB, it means the complex operator S. We're going to use this line. Based on this line, we are using the command TF, that is the command transfer function, to define in this case the transfer function that we want to use. For MATLAB, if we use this notation, this command here, MATLAB is going to understand that each time that we call the variable S refers to the complex Laplace operator S. That's the way to set MATLAB, this is my complex operator. If we want to model any transfer function, we always have to use this line in order to define the complex Laplace operator S. We cannot do it without this command, and this command is included into the control toolbox. Once we define our complex operator, we can define our transfer function, as we can see on the next line. You see here G is equal to 1 over R times C times S plus 1. It's pretty straightforward. Using this definition, translate or implement in MATLAB code the transfer function of the transfer function that you have, in this case, the RC circuit one here. All right, so here we just define our transfer function for a given values of R and C. Now the next step corresponds to plot or simulate the response of this RC circuit in the presence of a DC voltage power supply, in this case when EIS is equal to some voltage. For our case, EI will be 5 volts. This will be our input voltage, 5 volts. Considering that the simulation or the response of the RC circuit is given on time, as we can see here, we have to define at the beginning a vector. In this case here, this vector that you see corresponds to a time vector. I'm going to simulate the RC circuit from 0 to 5 seconds. with small steps of 0.01. That's the main idea here. Then we are going to create the EI voltage input. In this case, the EI voltage input is equal to 5 times ones. Ones create a vector of ones or an array of ones with one row and the number of columns corresponding to the number of steps for this vector t, the number of elements of t. In that sense, the size of our input will be the same as our time value, as our time axis. Then, to simulate the response of the system, considering that our RC circuit is a linear time invariant system, we can use this command that is called lsim. This command lsim basically gives you have to define your transfer function, that is g, that we already defined before, the input that corresponds to a constant 5 volts level, and tick that corresponds to the time axis that we want to, the time that we want to simulate this RC circuit response. Next, after we define this, the lsim command is the one that is going to calculate, in this case, our interest variable. Our interest variable, what is? The voltage in the capacitor. That is essentially the relationship that we are performing here using the transfer function. Therefore, we are going to plot the time response of the RC circuit. Now that with the LC command, we simulate the time response of the cost of the transfer function. Then we came here and we said plot. Plot is the Matlab command for plotting. We plot the voltage of the capacitor with respect to time, and this is just for axis. Those are just the axis x that corresponds to time, and the capacitor voltage that in this case is V of volts. Let's going to introduce another one here. Let's set hold on. And once we have hold on here, we're going to make another plot. It's going to set T. And the other one is the reference voltage, that in this case corresponds to 5 volts. Okay. So for now, let's do it this way. You see that my script in the bottom is yellow. This is because I'm separating my code by sections. To do that, simply add this double percentage symbol that corresponds to comment. Just put twice and then give a title. You see the title is bold for this section. And then I have another different section here of the code. So here you can just execute. To execute just this section, if you can execute the whole script using the run button, or you can execute just this section using this button, run section. Okay, now I'm executing the code. As you see here, we have the response of the system. In this case, for 5 seconds, the blue curve corresponds to the capacitor voltage, and this orange line corresponds to the system input. However, we can even improve this graph. How? We can came here and we can add legends in order to set which signal corresponds to which one. One is VC, that is the blue one, and the second one is EI, that corresponds to the voltage on the system input. Also, we can add some, for example, in y-axis, y-lim, we can define the limits for the x and y-axis. Let's going to set that y-axis is 0 to 6 in order that you can see the input of the system. And we can also define x limit that correspond in this case, for example, from 0 to 3. Originally, the simulation runs for 5, but we can shrink the graph that we want to represent. If we go again, you see, now our graph has shorter x-axis just because we introduced the limits. And here we see the voltage input of the system and the time response. If we calculate, in this case, the system tau, here we can see the transfer function, that is basically g. Our time constant tau is 0.2 seconds. Our system reached around 1 second, reach the steady state value, or the same input of the system, 5 volts, which corresponds to approximately 5 times this 5 times this time constant, 0.2 times 5, so we'll have around 1 second that we reach the steady state response. All right, so let's do a different test. In this case, as you can observe here, the test only works for one constant voltage, one constant input voltage, and in this case the capacitor basically reached the steady state. But what happens if after some time I remove or change the input voltage of my RC circuit? It means now it's not 5 but 0. I should see this behavior here. I should see this decaying rate. In order to simulate that behavior for going down, we're going to create a more complex input signal for the same simulation system. In this case, the simulation use the same transfer function. The only thing that we are going to change is this EI value here. So we are going to define a longer time simulation time, 10 seconds. Our signal EI is going to have 2 states, one high state, another low state. One of these states corresponds to 5 volts. The other state corresponds to 0 volts as input of our system. Basically, as you can see here, EI is composed by one high state, 5 volts, and another low state that is 0 volts. If we simulate this, like using the lsim command, we have G, EI, that is our new input, and T, that is our new time vector. And here we have the plot, which is pretty much the similar considerations that we do in the previous slide. Now I'm going to run just this section, using the run section button. Okay, now you can see here we have one high state, 5 volts. We have another low state, 0 volts. Here we have the time response, again around 1 second to reach the steady state. And here, once we remove the input voltage from the system, the capacitor starts to lose load. And in this case, again, about around it starts losing power at 5 seconds. So around 6 seconds is going to drain all the power from all the voltage from the capacitor. So here you can see that we can simulate a more complex input for the same system, and so that we can do the same for multiple inputs like sinusoidal or impulse responses. But these new inputs will be the topic for the next laboratory. For today, at this time, we want to observe and determine how to run this simulation. All right, now that we see how to implement the RC circuit in Matlab and simulate its response against different type of inputs, we're going to do the same, but using Simulink. In this case, this is the representation using Simulink with the transfer function block. And this is the response, which is pretty similar to the response that we obtained before. So how we are going to use Simulink and how Simulink works. To do that, we can came here to Matlab. I'm using Matlab 2019B. If you download the last Matlab 2020B, you will find exactly the same interface. So if you came here to Home, you can find Simulink here. Simulink, by its definition, is a ODE solver. So Simulink is a program that solves ordinary differential equations. In that sense, and it's based on a block-based programming language. So everything that we're going to place here with Simulink is based on block simulation, which could be a little bit different from our traditional way to coding, like into a script. But you will see that in the case of controls, it makes much easier to model and materialize your ideas, especially if your system is really, really complex. So once we are in Simulink here, let's go to blank model, and we are going to create a totally blank representation, a totally blank canvas to work. All right, this is our blank canvas for Simulink. Here we have some elements, like for how long we want to simulate our system. This time is in seconds. Run button, and a lot of options that we could have and use to debug our system. For today, we're going to keep it simple. We're going to increase the number of blocks and the complexity of the simulation as we go forward with the course. But for today, let's going to simulate the RC circuit. We're going to use Simulink to simulate the RC circuit in two ways. One is using the transfer function, and the other one is building the ODE that represents the RC circuit as we see before. So let's begin with the Simulink transfer function. So this is our transfer function. You see here, transfer function first order, and some blocks here. This is the input, and this is a block called scope. Let's going to drop all these blocks here from the library browser. If you need to find any block, you just came here to the library browser and search for the block that you need. Usually for controls, most of our blocks are going to be located in continuous, math operations, sinks, source, and signal routing. As we advance with the course, we are going to use most of these blocks. So you are going to be more familiar with everything here. For example, let's go to continuous. In the case of continuous, we have a lot of blocks for control: PID control, integrator, state space, zero, transfer function, delays, derivatives. We have all the blocks that we need for controls. So we need, in this case, a transfer function block, because we're going to use the RC circuit transfer function to represent it. So you came here and drag the block over the canvas of Simulink. You see, now we have our transfer function block. If you want a match, I mean, you see, you can make the zoom smaller, but you can pushing space bar, you can fit your content to your screen. This is a really good feature using spacebar. Here we have our transfer function. If we go behind, our transfer function here corresponds to 1 over RCS plus 1. You see that is pretty similar? Let's go inside. Let's go to change the parameters of this block in order to implement the transfer function. If we double click on the block, we see that the transfer function has numerator and denominator coefficients. In this case, the coefficients correspond to the polynomial in the numerator and denominator. For our case, the numerator, the polynomial, is 1 because we just have one gain, so there's no much problems over here. On the denominator, for the other hand, this one here corresponds to this one here. And this one here, the next one, this one over here, corresponds to the coefficient that came with this S. In our case, the coefficient that came with this S is RC. So we're going to replace this pole using the different values, that the values that we choose for the simulation. In this case will be 2 power of 3, 2k ohms, times 100 e power of minus 6. This is R, this is C. So our system will be 1 over RCS. If we replace, it's quite huge in this case. However, we can make a better representation. We can represent this in a different way. You remember that this coefficient corresponds to 0.2, the multiplication of R and C. Let's set, you can create annotations. You can just double click here and you can set R is equal to 2 kilo ohms. Let's add again, create annotation. R is equal to 2 kilo ohms. And C is equal to 100 microfarad. If we make this product, our transfer function will be 0.2. The coefficient that goes here times RC or tau will be 0.2. Now, let's going to drop other blocks. In this case, we need an input block. So we can came here to library if we are in this shrink view. We came to the library, we go to source. We have many different sources to excite this block. So we have constant, chirp signals, a lot of different inputs that we could use. Ramp input, pulse generator, even inputs directly that came from signals from the workspace. So for today, we're going to use just a simple constant. Okay, this is my simple constant. This constant has the value of 5. We're going to rename this one EI, that corresponds to the input voltage of the capacitor. If we want to join the input of this block with this one that represents the input signal, we just drag from this block to this one, this arrow. Basically, I'm going to do again. We do in this way. We can reduce this, can reduce the size if we want. Also, that's possible. Okay, now we put some input to this block. Now we want to see the output of the block. To see the output in Simulink, we came here again to the Simulink browser, and here we put the scope. A scope basically is like the scope in the lab, where you can see the signals changing. Here is something similar. All right. This is a scope, that this is a plot, time versus the amplitude of the signal, in this case the output. And that's it. This is what we need to run the simulation. Before running the simulation, let's going to verify some things about Simulink. To run the simulation, we just need to push here the run button. However, we can decide how long we want to run our simulation. 10 seconds, 1000 seconds, whatever our system requires. In our case, let's going to keep for now 10 seconds. And now let's go and execute the simulation. Once we execute the simulation, we can see the system response here. As you can see, the response is the same as we obtained with Matlab. You see here that at 1 second we reach the steady state value for the Rlc circuit, which is really good, and our system works in this case. We can make some style editions for this scope. Like for example, we can change the background as well as the lines color, just something like this. And you can have a neat representation. Here I'm just making zoom with this tool here. Our simulation runs for 10 seconds. However, we can reduce the time that our simulation executes. For example, let's go here, let's set 3 seconds, and let's run again. You see, now the total simulation time is 3 seconds. But the behavior of the system is the same. We are just reducing the amount of time that we want to run the simulation, just for this RC circuit block that we have here. All right. So this is if we want to simulate the block, in this case the Simulink transfer function. However, I guess what we want more is using the ODE, because one of the main capabilities of Simulink is simulate ODEs and PDEs and solve them numerically. For the RC circuit, we can solve by hand, but if the system is really complex, we cannot just solve the problem by hand. So Simulink is going to simplify our modeling and design task. Let's think in the ODE for this RC circuit. This is the ODE simplified and factorized. In this case, the derivative of the voltage over the time is equal to 1 over RC, 1 over tau, the input voltage minus the voltage on the capacitor. That is our output. Okay, so I'm going to use the same block diagram in order to show you that we can add more elements as we want to our simulation. However, in the first attempt that we do to simulate with Simulink, the transfer function, we use this block. In the case of an ODE, as you can see here, it's quite different perform that operation, especially because we have the derivative operator here. Whenever we have a derivative operator, what we should do is came here to library, go to continuous, and you will see this block that corresponds to integrator. Let's going to drop this block here first. What makes this block for us? Let's set x prime here, and let's set here x. Let's set here x as annotation. I just copy this thing here. What integrator makes is basically integrate numerically a signal. In this case, the input will be the derivative of that signal, and the output will be the integral of that signal. In this case, if we see here, we have, for example, the derivative of the voltage of the capacitor regarding to time, and here the ODE has voltage of the capacitor in the other side of the equation. So using our same notation, we will have this thing here, PC prime, and this will be PC. So you are wondering how we are going to implement this. So let's do in this way. First of all, what we want to see is this variable, right? VC. We don't want to see the derivative. We want to see is the voltage on the capacitor. So let's go here. Let's going to, you see that inside this equation, I mean, this side of the ODE is the derivative of the voltage. So this side of the ODE corresponds to a subtraction. We can add blocks in this case for subtraction and mathematical operations. We can come here to math operations, and we have all the operations that we want that we need. I'm going to drag the add block. Let's put here that block for now. One of these blocks will be plus minus. You see, now we are making a subtraction. The first input has is positive sign and the other one negative sign. The negative sign corresponds in this case to the voltage of the capacitor. Therefore, we are going to create this feedback loop that we are looking here. And then we are going to add a constant. I forgot to mention this trick yet, but if you know the name of the block that you want to put on your workspace, you simply need to put your pointer and make click over your canvas and set, for example, constant. Simulink is going to give you a list of blocks with the same name. For our case, let's drag the constant. Okay, this is just an error. We can do the same, for example, with transfer function. You see, I invoke the transfer function. Even we can do the same with scope. So this is a good trick that is going to save us a lot of time. All right, so if we see here, basically the derivative or VC prime is the subtraction between EI minus the voltage in the capacitor VCT. But also we see that we need a multiplication, 1 over RC, that corresponds to 1 over tau. We can do this multiplication in two ways. One way is simply use the multiply block, use the product block, sorry, this is one way, the product block, and we can put this block here and take a constant again. Let's type constant, and we can make the multiplication 1 over tau, that is 0.2, and we can put here. In that sense, what we need now is a scope to see the response of the system. In this case, for us, this will be our VC, and this case will be our VC prime. Let's simulate the model right now. As you can see here, the response of the system is pretty much similar and pretty much consistent. It's exactly the same than the previous one. And basically, we are building the system in this way. However, we can use another way to perform this multiplication that is more nice in the sense of clarity of our block diagram. I'm going to select my whole block diagram here. I'm going to make a copy, Control C, Control V. And now I'm going to replace this one. And to replace that, I need a new block. This block is called gain. And we put this gain in series with this block here. This gain is exactly the same that we have here, 1 over 0.2. That corresponds to 1 over RC. I'm just extending this one. Let's go to run again the simulation. Now you see that the response is pretty much the same. Now, if I want to compare two outputs in the same scope, I can do the following. I can call a new scope, and I can use something called multiplexer or MUX. And the multiplexer is going to take the signals, is going to put together into one channel. And once I run the simulation, you will see that in this case, both of them are overlapped because the simulation has the same response. All right, so let's go into make a final step just to finalize this tutorial. We have here the transfer function representation. We have here the ODE representation. And why we use the ODE representation? Because with the ODE, we can consider the initial conditions of the capacitor voltage, which is a really common situation on real life. With the transfer function that we made here, we are assuming that our initial conditions are 0. But here, because we have this integrator block, we can just simply change the initial condition where we want that our system starts. I mean, the voltage is not always 0. Could start between 0 and 5. That is our possible voltages. So I'm going to take here, for example, in this one, I'm going to put 0. For example, I'm going to set 3 volts. And to illustrate you, let's going to set here 2 volts. Now, before to proceed with the simulation, let's going to change the input of the system. In this case, let's going to use 5 volts, similar way that we use on the initial simulation with transfer function. And then let's going to run the simulation again. In this case, I'm going to open the scope and I'm going to run the simulation from here. It's essentially equivalent. As you can see here, the simulation in one case starts from 2 volts and the other one starts from 0.3. According to that initial condition, of course, our dynamical response is going to change a little bit. However, our settling time is more or less the same, at least for this simple system. But the initial conditions will have a significant influence over the final performance of our system. So that's it. This is like how we can create really simple simulations with Matlab Simulink of dynamical system, in this case using the Rlc circuit. If you have any questions, just make it during the lab season or during the office hours. Thank you so much for your attention and see you on the next. All right, so this was the tutorial for Matlab Simulink. This tutorial is trying to be as much comprehensive as possible in order that you can get some of the basic skills for simulating dynamical systems. I received some questions during the reproduction of the video. You can watch again this video. Here is the link. You can watch whatever time you need. Just you access over here and you can watch again and again. I received another question about how to make this connection. This block here is the multiplexer block. This multiplexer block basically is going to put many signals together in order that this scope can show all the signals that we have. These MOOCs can be, I mean, by default, Matlab put 2 inputs, but if you double click on the MOOCs block, you can add as much inputs as you need, from 2 to whatever you need. Okay, we get some other comments. Another comment that I get is if we can add a title to the Matlab Simulink blocks, and the answer is yes, we can. And the answer is yes, we can. Just let me do let me show you a really quick how to do it. I'm going to stop sharing this. I'm going to share a different one. This is like a blank Simulink canvas. Let's set, for example, constant I'm going to add a couple constants here. Let's say this is 5, the other one is 1. Let me add another one, like 10. I'm going to add a scope, just as we see before. I'm going to add the mux. I add the mux. In this case, I want to put those 3 signals on the mux. We just simply double click over the mux multiplexer block. And I set 3 because I need 3 inputs. You can extend the block as you need. Just put here and here and here. My simulation time, 10 seconds. Just keep that in this way. Let's go into execute the simulation. I double click the scope. If you see here, you can start the simulation from here is equivalent that starting from here. Okay, so in this case, we find something interesting because those are constants. Simulink only displays 1 point at the beginning. So let's change that a little bit. We can came here to the style. We can came and set like, if you don't like the black background, you can use just simply white background and green lines. You see that we have okay, let's apply this. We have a yellow marker, a blue marker, and an orange marker. Let's set something like that. Okay, maybe not in this way. I'm going to change the last marker. It's not too clear. Okay, maybe not this color, maybe this one. Still too soft. Let's put red. First marker, second marker, third marker. If you want in this case to change the axis configurations, let's set, for example, here, let's go to configuration properties. You can came to time. You can set, if you want to show the label of the x-axis, you can click this option and you will see time. And for the y-axis, you can here define the y label, like let's say, I'm going to put some number iterations, or let's set voltage in volts. Let's apply. Now we can add the axis, and we can also add title to a figure, like sample figure. By default, always in Simulink, your x-axis will be time by default, and your y-axis will be the amplitude of some waveform that of the signal that you are analyzing. I'm going to change these constants. Let's put something more interesting. I'm going to use a block called signal generator. Let's copy the block. You can click over the block and then use right click and drag below and replicate the same element. This signal generator can produce different type of signals, like sinusoidal signal. Let's use the other one, a square signal, and let's produce the other one, the sawtooth signal. You maybe can see this a little bit better. You see, now we see signals on Simulink, which looks much better. One is sinusoidal, another one is sawtooth, and the other one is just square signal. We can edit these signals again. We can come here to style. We can remove those markers if you don't want to watch it. You can change here which line you wanna use. I'm just removing the markers to see clear signals. We can also add legends. We come here to view and click on legends. We can change the name of the legends. We just simply need to change the name. We can double click these wires, for example, and let's set like sine wave. This is square wave. And the other one in this case is sawtooth wave. You can move these labels. Will be exactly the same cable, just we put in a different place. Click over here. You see now the legends changes. So those are some ways that you could use to improve the presentation of your graphs. All right. So this is just one simple example how you can improve your Simulink results. If you have any other question from the tutorial, please feel free to do it. Right now, you are going to work on the lab assignment. The first part, basically, you have to replicate the tutorial and then replace the values of R and C in order to see what happened. That's the first step of the lab. In the second step, you are going to do the same, but with a more complex circuit, in this case, the Rlc circuit. And you are going to change the parameters of R, L, and C. So that's the last assignment. Please start working on that. We are going to be here during these 3 hours. So anytime you have a question, just raise hand or text through the chat box and we can solve the questions. So please start working, and again, we are open to questions from this moment. Yes, each time if we change the circuit, we have to use the same plots. That's the basic idea. Use the same plots in both, for both circuits. Yes, in the case of Matlab code, you put the code as an appendix at the bottom of the report. In the case of your Simulink diagrams, put as figures on your report. Figure 1, like this is my Simulink block, or figure 2, this is my Simulink block. For the Matlab codes, just put as an appendix in the bottom. It's okay. Any other question? All right, so now please start working on the lab. We are going to be here. So any question, we are still open. For those who need to install the control toolbox, you can do two things. Let me just share my screen to show you. This is my Matlab. This is my Matlab. I don't know if you can see it. Once you are in Matlab, you came here to this tab called Apps. You can see here, mine has several, but here you can see this one, Control System Design and Analysis, Control System Designer. This corresponds to the control toolbox. If you want to install some specific app, you came here to Apps, Get More Apps. And once you, if you don't have installed the control toolbox, you just set here Control Toolbox. My case, for example, said Control System Toolbox already installed. I'm going to click here, but if you doesn't have, you will find here the button to install. Let me show you an example. For let's say this toolbox. You see, you will see this button install. This is a different one. This is audio toolbox, but if you don't have the control toolbox, you will see this button called install. So that's the easy way to add the toolbox that you don't have. If you are using MATLAB 2019 or 2020, you can add easily in this way. The other way is you just download the MATLAB installer from the website. And at the beginning of the installation, you choose which toolboxes you want to install. This is that I was trying to, what I was trying to do. Basically, I just want to show you with the installer. I'm not going to do the installation, of course, I already have MATLAB installed, but I just want to show you when you install MATLAB, where you choose the toolbox that you want. Okay, it's taking some time to unzip it. You put your user set email. Okay. Let me fix that. I forget my password. I just need to restart it. Okay, I just go with my license. I said yes. Undergrad student or grad student in this case. I choose my license. Okay, let's say yes. Let's say yes. Okay, I have to log in with my UC Merced. With my UC Merced ID. Okay, let's wait a little bit, that Matlab process. Okay, I have to shut down my Matlab just for now. Okay, now it's closed. Now I guess I can proceed. Let me go to a different location. Did I just close my Matlab? Okay, now here is the most important part. When you install Matlab, you will see a lot of toolboxes available for us as UC Merced students. Here is the control system toolbox and all of the toolboxes that you have that you want. Even that includes also a Simulink. So my recommendation for all of you, when you are installing Matlab, just install everything that you have. Sometimes you need some commands from a different toolbox and you don't, and if you are going to use it, your code is not going to work. We are going to need combination of multiple commands of all the toolboxes, at least most of them. So my recommendation is once you install Matlab, install all the toolboxes that you have available. In that sense, you don't have that problem with the commands in the future. And then once you choose all the toolboxes, you choose next and then continue the installation. I'm not going to do right now. I already have my Matlab in my computer, but this is the way to proceed. Just install all the toolboxes that Matlab provides you.
question. Can I share my screen?
No, I'm not. Okay, let me. Okay, are you sharing your screen? One?
Let me see.
I don't think you are. Okay,
Can
now
you
you
see
are
it?
sharing screen, yes.
So when I run it, I do get a correct response from the first section, but for the other two, I just get straight lines. So if I
Okay,
run it,
show me, please.
this is the correct response.
I'm not seeing the scopes.
Oh wait, let me see if I could try to. Let me see.
Maybe you can share your whole screen, not just Matlab.
Let me see how I can do that. This is the response I get from that one. And then for the other response, for these two responses, I get a similar response, which is just a straight line. Are these two setups correct?
I think in the bottom one, the one is 5.
Oh, this one, yeah.
Yeah, that one is 5. Can you check the initial condition for your integrators? Double click on the integrator block. 1/s block. I can. Okay.
Oh, wait, let me see if I can.
Double click again, please. Yeah, initial condition 0, and the other one is initial condition 0. Can you extend? Okay, but that should be correct.
This is the response I get when I run it.
Can you show me the mux, the multiplexer?
The multiplexer, yes. Where is it?
The scope. The scope, sorry. Can you show me
Oh,
the
this
scope?
one?
Yeah, please.
Okay, let me try. Let me see. Can you see it or?
No. I think you are just sharing your Matlab. Maybe when you do screen sharing, you can check below the.
This is the response I get from.
Go to next to the aim in the top bar, to the left. Left.
To the left.
You see this two bar. No, go more to the right. In the second bar, not the no, below.
Okay,
No, not
right.
yeah. You see this the scope, the magnifying lens.
This one?
The next one, not that one, but the next one. Click on the next one, please.
This one?
Yeah, click there.
Oh, okay.
This is just shrink your that adjusts the scale of your scope.
Okay.
Probably you need to do that to every time you run your simulation, you use that in order to see which is the amplitude of your signal.
Okay, yeah, that makes sense.
Because in the other sense, you see that was power of 23, so that's the reason why you have like a straight line.
Okay. All right, thank you.
Welcome. I launch another pool. Another poll. Please answer as much with as much honest as you can, please. I see your diagram, but I don't understand your question.
Can you hear me?
Now I can hear you.
Okay, yeah. So I hit run, and then I'm not getting anything.
You have to click on the scopes.
You have to click on them individually, or just
Click, for example, that scope.
this one?
Yeah, for example, click that one. No. Okay, I mean, you just double click on the scope, and you should be able to see the.
Oh, I see. Okay, gotcha.
Okay.
So this is, you want us to get a diagram for each individual one, or do you want us just to get like the whole?
You can report 3 of them, and then the combination of all of them.
Okay. Well, thank you.
You're welcome. If anyone has class at noon, please feel free to disconnect. We will stay here from up to 12, but if you need to attend another class, please, you are free.
I just have one quick question.
Sure.
For the MATLAB plots, because you said we have to do the one that's in the video, and then also the one with the new values.
Mhm.
Should we include the like steady lines at 5 and at 0 in the extra, in the ones with the different values as well?
You mean the input value?
No, I mean, like, when we plotted the let me.
The voltage of the capacitor, right?
Yeah.
Yeah, that's okay. Just the voltage of the capacitor. You don't need to include the reference.
Okay, and I put all three in one plot, in one figure. Should I have, is that fine, or should I put different figures?
For the
Please.
reproduction, for the new condition, yes, you can put all of them on a simple graph. For the reproduction, please include the separate ones.
Okay, I got it. All right, thank you. So
You're
that's all I
welcome.
have. Have a nice day.
Okay, have a nice day.